Module 5, Lecture B, Using Functions Well. By the end of this lecture, you will be able to design functions that perform a single clear task to improve readability, separate user interaction from computation by structuring code into helper functions, and reuse functions across different parts of a program to reduce duplication. Clear function design. Single responsibility principle. The single responsibility principle says that each function in your program should do one clear, specific task. When a function focuses on a single job, such as calculating a discount or formatting a date, its behavior is easier to understand, predict, and explain. This focus reduces mental effort for the programmer and makes the code more flexible. By keeping functions narrowly targeted, you create simple building blocks that are easier to maintain and reuse throughout your program. When a function tries to handle many different tasks at once, such as gathering input, performing calculations, and producing output, it becomes complex, hard to understand, and easy to break. In this state, a small change in one part of the function can unintentionally affect other parts. By giving each function a single clear responsibility, you keep the code simpler and more reliable. This makes it easier to modify one function without risking unexpected problems elsewhere. To follow the single responsibility principle, regularly check that each function has one clear purpose and delegate extra work to other, more focused functions. For example, in a library system, separate functions might handle checking availability, calculating late fees, and updating accounts, and in data analysis, different functions might clean data, compute statistics, and generate reports. When a function starts doing several different tasks, treat that as a signal to split it into smaller, single-purpose functions. This leads to code that is clearer, more logical, and easier to test and extend. Python code, single responsibility principle. In this lesson, you should first show one long function that clearly violates the single responsibility principle by trying to do too many things at once. Then refactor that code into several smaller functions, each with one clear and focused responsibility. After that, compare the outputs and structure of the original and refactored versions to emphasize how the smaller, well-defined functions improve readability and maintainability. If your example requires external tools, briefly mention installing any needed library with the appropriate package manager command. The function first computes the total cost before tax by multiplying the item price by the quantity. It then calculates the tax by multiplying this subtotal by the tax rate expressed as a percentage. The tax is added to the subtotal to get the final total after tax. The function prints a brief message about processing the order, including the item count, the price per item, the tax rate, and the final amount due, and then returns the total after tax. This function focuses only on calculating the total cost of an order. It first finds the subtotal by multiplying the item price by the quantity. Then it computes the tax by taking the subtotal and multiplying it by the tax rate divided by 100. Finally, it adds this tax amount to the subtotal to get the total cost after tax and returns that value. This clear separation of steps keeps the function focused on a single responsibility. This function creates a clear, formatted summary of an order using 4 inputs: how many items were ordered, the price of each item in dollars, the tax rate as a percentage, and the total cost after tax. It builds a single string that includes all these details and formats the price per item and total cost to 2 decimal places for readability. The function then returns this string so it can be used elsewhere in the program to display the order summary. Its only job is to format this summary, which follows the single responsibility principle. This function prints an order summary based on a single input, the summary text. First, it announces that the order is being processed, emphasizing that this function has one clear responsibility. Then, it prints the summary details themselves. By separating the message about processing from the actual order details, the code follows the single responsibility principle and becomes more modular and easier to maintain. The script first checks that it is being run directly, so the main code does not execute when imported. It then calls one function that processes an order and handles everything from calculation to printing. After that, it uses a separate function to compute the total cost after tax, and another function to create a formatted order summary using the quantity, price, tax rate, and total. Finally, it passes this summary to a dedicated printing function. This structure demonstrates how separating responsibilities into focused functions improves code readability and maintainability. This script illustrates the single responsibility principle by contrasting a single, all-in-one order processing function with a refactored, modular design. In the original version, one function calculates the total cost, adds tax, and prints all order details, mixing several responsibilities. The improved version separates these concerns into distinct functions. One computes the total cost, another prepares the order summary, and a third handles printing. Both approaches produce the same numerical result, but the refactored design is clearer, easier to maintain, and less error-prone because each function has a well-defined role. Naming functions clearly. When naming a function, choose a clear, precise name that states exactly what it does and what it does not do. Focus on a single specific action or result, such as calculating a value or transforming data, and use verbs and nouns that describe that action. Imagine explaining the function in one sentence to a colleague. Then use the keywords from that explanation in the name. For example, if a function cleans survey responses, its name should mention both cleaning and survey responses, so its purpose is immediately obvious, even to someone new to the code. Clear function names can reveal when a function is trying to do too much. If you need a long, clumsy name that combines several actions, that is a sign the function should be split into smaller, focused ones. For instance, instead of one function that loads, validates, and saves user data, create separate functions for each task. This keeps names short and precise, improves readability, and makes testing and debugging easier. When each function has a single, clear purpose, you can rely on its name to accurately describe what it does. Consistent naming in a project makes code clearer and easier to navigate. When similar functions follow similar naming patterns and use the same vocabulary, understanding one part of the code helps you understand others. For example, in a financial app, All fee calculation functions might share a common naming style, and in scientific simulations, functions that update parts of a model can follow a similar pattern. Over time, this consistency creates a shared language for the team, improving communication and making it easier to spot mistakes. Python code. Naming functions clearly. This material emphasizes the importance of clear function names when writing simple temperature conversion code. Instead of using confusing or vague names, each function should have a descriptive name that makes its purpose obvious. By comparing unclear names with well-chosen ones, you can see how good naming reveals exactly what each function is responsible for. Clear names make code easier to read, understand, and maintain. This comment explains that you do not need to run any pip install commands for this script because it only relies on Python's built-in features. In other words, it does not use any external libraries. As a result, the setup is simpler, and the script can be run without installing additional packages. This function is poorly named, so its purpose is unclear. It takes a temperature in Fahrenheit, converts it to Celsius using the standard formula of subtracting 32, multiplying by 5, and dividing by 9, then prints the converted value with a label. It also returns the Celsius result. Because the name does not describe this Fahrenheit to Celsius conversion, it can easily confuse someone reading the code. This function is designed to convert a temperature from Fahrenheit to Celsius. It takes a single input, the temperature in Fahrenheit, and applies the standard conversion formula by subtracting 32, then multiplying by 5 and dividing by 9. The result of this calculation is the equivalent temperature in Celsius. The function then returns this Celsius value so it can be used or displayed elsewhere. This function classifies how a temperature in Fahrenheit feels using simple thresholds. If the temperature is below 50 degrees, it is labeled cold. If it is 50 or higher but still below 77, it is labeled comfortable. Any temperature at or above 77 degrees is labeled hot. In this way, the function converts numeric temperatures into intuitive descriptions of how they feel. This example shows how unclear function names can make code confusing. We first print a message to signal that we are using a poorly named function. Then, we call a function with an ambiguous name that takes a temperature of 68 degrees Fahrenheit, converts it to Celsius, and prints the result, even though its name does not reveal this purpose. The converted value is stored in a variable with another vague name, emphasizing how unclear naming can hide what the code is actually doing. We use clearly named functions, so the program's output is easy to understand. First, we call a function that converts a temperature of 68 degrees Fahrenheit to Celsius and store the result. Then, we call another function that takes the same temperature and returns a description of how it feels. Finally, we print a message that combines the Celsius value with the description of the temperature, creating clear and readable output. This script shows why clear function names matter in Python. It begins with a poorly named function that converts a Fahrenheit temperature to Celsius and prints the result, but the name does not reveal its purpose. The improved version uses one clearly named function that returns the Celsius value and another that describes how the temperature feels, such as cold, comfortable, or hot, based on the Fahrenheit input. Using these descriptive names makes the output easier to understand and the code's behavior more predictable. Writing short functions. Writing short functions helps keep your program manageable by making each part easy to understand at a glance. When a function is concise, you can quickly follow its logic and confirm it does exactly what it is supposed to do. This style encourages breaking a large task into smaller, independent steps, such as separate functions for loading, cleaning, analyzing, and formatting data. Together, these focused pieces form a clear and organized flow for your program. Keeping functions short and focused on a single task makes it easier to find and fix errors, which improves code reliability. When a function is long and handles many responsibilities, bugs can be hidden and it becomes difficult to connect specific inputs to the outputs they produce. By separating tasks, such as payment validation, shipping calculation, and inventory updates in an online order system, you can quickly locate where a problem occurs. This structure reduces complexity, simplifies debugging, and makes ongoing maintenance more manageable. Short, focused functions make teamwork and code evolution easier by clearly separating responsibilities. In a collaborative project, one person can change the function that calculates discounts without risking unintended changes to something like email notifications. As requirements shift, these small, well-defined functions are simpler to update or replace, such as swapping a basic data cleaning step for a more advanced one. This structure keeps the software clearer, more adaptable, and more reliable over time. Python code, writing short functions. In this lesson, we will show how to break a long, complicated task into short, clear functions. We will first look at a messy version where everything is done in one place, which makes the code hard to read and maintain. Then we will improve it by splitting the work into small, focused functions, each handling a single part of the task. The goal is to keep everything simple and beginner-friendly, so you can clearly see how shorter functions make your programs easier to understand and work with. This line is a reminder to install any libraries the code needs in order to run. It acts as a placeholder showing where you would use a package manager to add required dependencies. Including such a comment is common practice to make sure all necessary tools are available so the script can function correctly. This function computes the grand total of an order in one combined calculation. It first adds tax to the subtotal by applying the tax rate, then calculates the tip as a percentage of that same subtotal. It also adds a fixed service fee of $2.50. Finally, it adds the taxed subtotal, the tip, and the service fee together, and returns this overall total cost. This function calculates the final amount after tax is added to a subtotal. It takes the subtotal in dollars and a tax rate given as a percentage. Inside the function, it multiplies the subtotal by the tax rate divided by 100 to find the tax amount. It then adds this tax to the original subtotal and returns the total, which includes both the original amount and the tax. This function calculates a tip based on a bill subtotal and a tip percentage. It multiplies the subtotal in dollars by the tip percentage, then divides by 100 to convert the percentage into a decimal value. The result of this calculation is the tip amount. The function then returns this tip amount so it can be used elsewhere in the program. This function adds a fixed service fee to a given total. It takes the current total in dollars and a service fee in dollars, then calculates a new total by adding them together. The function returns this updated total. Using this design makes it easy to change the service fee later without modifying the main program logic. We define a main function to compute the final order total by combining several smaller helper functions. It first calculates the subtotal with tax using the given tax rate, then computes the tip based on the subtotal and the chosen tip percentage. The tip is added to the tax-included total, and finally, a fixed service fee is added. This modular design breaks the calculation into clear steps, making the code easier to understand and maintain. In this example, we set up simple values to show how an order total is calculated. The subtotal is $40, which is the starting amount before extra charges. We then apply a sales tax rate of 8.25% to this subtotal to find the tax. We also use a tip rate of 18% based on the same subtotal. These values are used to demonstrate how the final total is computed using both a messy function and a clearer, more organized function. We use a long, messy function to calculate the final order total. It takes the subtotal, the sales tax percentage, and the tip percentage as inputs. The function adds the tax amount, the tip amount, and a fixed service fee to the subtotal. The result, called the messy total, is the grand total that includes all charges. We calculate the final total by using a main function that calls several smaller helper functions. This main function takes the subtotal, the sales tax rate, and the tip percentage as inputs. It then combines these values to compute the final amount owed. Organizing the work into clear, focused helper functions makes the code easier to read, understand, and maintain. We display the total produced by the messy function so we can compare it with the clearer version. The program prints a label that says messy function total dollars, followed by the calculated amount. This amount is rounded to 2 decimal places, so it is easier to read and looks like a standard currency value. We display the final total produced by the clear short functions to verify the result. The message announcing the clear short function's total in dollars is shown, followed by the total amount. This value is rounded to 2 decimal places, so the dollar amount is easier to read and compare with other values. This script shows why it is helpful to break a complex function into smaller, focused parts. It starts with one long function that calculates an order total by handling tax, tip, and service fees all together, which works but is harder to read and maintain. The improved version replaces this with 3 short helper functions, each responsible for one step: adding tax, calculating the tip, and adding a fixed service fee. These helpers are then combined in a simple, clear function that produces the same final total as the original. By printing and comparing both totals, the script confirms they match and highlights the readability and modularity gained from using short, focused functions. Structuring programs clearly. Designing a main function. You can think of the main function in a program as a coordinator that controls the overall flow rather than doing all the detailed work itself. It decides the order of actions, such as getting user input, calling helper functions to do the processing, and then showing the results. This makes the main function a clear high-level description of what the program does, which makes the code easier to understand and change. For example, in a budgeting app, the main function would manage user prompts and delegate the actual calculations to other functions, keeping its role focused on orchestration. The main function serves as the central point for user interaction, while delegating calculations to helper functions. It greets the user, collects required inputs, and checks that the data is valid before sending it to other parts of the program for processing. In a study planner, for example, it might ask about courses, remaining weeks, and available study hours, then pass this information to helper functions that compute study time or build a plan. Finally, the main function presents the results clearly, keeping user interface tasks separate from the underlying logic and computations. Designing your main function to coordinate helper functions makes your program easier to test, maintain, and update. By letting the main function focus on orchestration, you can test the computational parts separately from user interaction. When the user interface changes, such as moving from text input to graphical input or to data from files or networks, you often only need to modify the main function while leaving the helper functions unchanged. This keeps the main function as a clear, stable entry point that connects how users interact with the program to the underlying computations. Python code, designing a main function. Design your program so that the main function clearly controls the overall flow. Keep user interaction, such as input and output, separate from the helper functions that perform the actual calculations. To illustrate this structure, you can use a simple budgeting example where the main function coordinates the process while dedicated helper functions handle the computation. This note explains that you do not need any extra installation steps for this script because it only relies on Python's built-in libraries. In practice, this means the code is simple to use and does not require installing additional packages. As a result, setup is easier and you can run the script right away in a standard Python environment. This function calculates monthly savings by taking income and expenses in dollars and subtracting expenses from income. The result of this subtraction is the savings amount, which the function returns. Using a separate function for this calculation keeps the program more organized and makes the code easier to update and maintain. This function estimates yearly savings based on a given monthly amount. It takes the monthly savings as input, multiplies that value by 12 to account for all months in a year, and uses the result as the projected yearly savings. Finally, it returns this calculated yearly savings amount. This function creates a summary message that shows both monthly and yearly savings. It takes the monthly savings amount in dollars and the yearly savings amount in dollars as inputs. Inside the function, it builds a single formatted sentence that includes both values. Each amount is shown with 2 decimal places for clarity. The function then returns this completed message so it can be displayed to the user. The main function controls how the user interacts with the budgeting calculator and When helper functions are called. It starts by displaying a welcome message that explains the purpose of the tool. This introduction helps the user understand what the program will do and provides a clear starting point for the program's flow. The program assigns a default monthly income of $5,000 and default monthly expenses of $3,000. These values act as fallbacks when standard input is not available and the program cannot ask the user directly. Using these defaults allows the program to keep running and still demonstrate how it works even without any user input. The code first changes the user's income input from text into a floating point number so it can be used in calculations. It does the same conversion for the user's expenses input. Turning both values into numbers is essential because it allows the program to accurately compute the difference between income and expenses for later use. The code first finds how much money is saved each month by using a function that subtracts expenses from income. It then uses another helper function to multiply this monthly savings by 12. This gives an estimate of the total amount that will be saved over a year. The program first calls a helper function that takes the monthly and yearly savings amounts and turns them into a single summary message. This function returns a formatted sentence that clearly describes the savings results. The program then prints this message so the user gets a concise overview of both their monthly and annual savings. The main function starts the budgeting calculator and manages the overall flow of the program. It greets the user, briefly explains the tool's purpose, and asks for monthly income and expenses, converting these inputs into numbers. Using these values, it calls helper functions to compute monthly and yearly savings. Finally, it creates and displays a summary message that clearly presents the user's savings results. This script is a simple budgeting calculator that uses a main function to organize the program's flow. It takes user income and expenses, which may be hard-coded when input is not available, then computes monthly savings by subtracting expenses from income. It next estimates yearly savings by multiplying the monthly savings by 12. Finally, it creates and prints a summary message showing both monthly and yearly savings, clearly separating user interaction from the calculation logic. Writing helper functions. Helper functions break a complex task into smaller, clearly named operations, each responsible for one specific job. Instead of one large block of code handling input, calculations, and output, each distinct action is moved into its own function. For example, one function might calculate ingredient needs, another might compute total cost, and another might format the final results. These functions simply take data, process it, and return a result without needing to know where the data came from. This creates a reusable toolkit of operations and keeps user interaction details separate and easier to manage. When designing helper functions, make sure they work independently of user input and output. They should accept clear parameters, perform data processing, such as computing totals or averages, and then return the result without handling any user interaction. In a study tracking app, for example, one part of the program might collect daily study hours, while a helper function simply processes the list of numbers. Another part of the program can then decide how to display the result, such as text, a progress update, or a chart. This separation makes helper functions easier to test, reuse, and adapt when user interaction changes. Helper functions let you adapt to your program to new environments without changing its core logic. For example, a text-based fitness tracker can use helper functions to convert steps to distance or estimate calories, and those same functions can later be reused in a mobile app or web dashboard. Even if the user interface changes, the underlying calculations stay the same. This reuse saves time, reduces errors, and keeps behavior consistent across different platforms. Python code. Writing helper functions. This lesson focuses on writing helper functions that clearly separate input from computation. You will see how these helpers receive data, perform their calculations, and return results in a clean and organized way. The goal is to keep user interaction, such as reading input, separate from the logic that does the calculations and from the code that formats the output. This separation makes programs easier to understand, test, and maintain. In this part of the script, we point out that pip install commands are not needed for this simple example. This means the code does not depend on any external libraries that must be installed separately. As a result, the script is self-contained, easy to run, and requires no extra setup. Stating this explicitly helps clarify that there are no additional dependencies to worry about. This function calculates the total number of minutes spent in a week based on a list of daily minute values. It takes the list as input and uses a built-in summing operation to add all the daily values together. The result is the total weekly minutes. The function then returns this total so it can be used elsewhere in the program for further processing or display. We create a helper function that computes the average number of minutes per day from a list of daily values. It first finds how many days are in the list, then adds up all the daily minutes and divides this total by the number of days. The function then returns this average. Organizing the logic this way keeps the calculation clear, separate, and easy to reuse in different parts of a program. The format summary function creates a short text description using two inputs, the total minutes and the average minutes. Inside the function, it builds a single string that includes both values with the average rounded to 1 decimal place. It then returns this string so other parts of the program can display or use the summary as needed. The main function starts by announcing that the study time helper is running, then creates a list of daily study minutes for a week. It sends this list to a function that calculates the total weekly minutes by adding all the daily values. It then sends the same list to another function that computes the average daily study time by dividing the total minutes by the number of days. Together, these steps show how to compute both total and average study time from daily data. The program calls a format summary function with the total and average minutes and stores the return summary in a variable. This function creates a clear, human-readable sentence that describes these values. The program then prints a message saying that the weekly study summary is ready, followed by the formatted summary text itself. The program begins in the main function, which announces that the study time helper is running. It defines a list of daily study minutes and sends this list to a function that calculates the total study time for the week. Another function then computes the average daily study time from the same data. A summary function combines these results into a clear message and the program prints this summary to give the user an overview of their weekly study habits. This script shows how to use helper functions in Python to keep input, computation, and output separate. It works with a fixed list of daily study minutes for a week, then uses one helper function to add them up and another to compute the average per day. A separate function turns these results into a short summary message. The main function then prints this summary, keeping user interaction clearly separated from the calculation logic and demonstrating clean, modular code design. Cleanly separating logic. In programming, it is important to separate code that interacts with the outside world from code that processes data. Interaction includes things like reading input or printing messages, while processing focuses on computations and transformations. When these are mixed in a single function, the code becomes harder to understand and maintain. By keeping them separate, each function has a clear role, which makes programs easier to manage, especially as they grow larger and more complex. You can think of a program as a dialogue between two teams. One handles communication with the user, and the other performs analysis and calculations. When you design functions, assign each one to either communication or analysis, but not both at the same time. For example, in an online shopping system, one function might compute the total cost with discounts and taxes, while another handles user prompts and displays. Keeping these roles separate makes the calculation function reusable across different platforms, such as mobile apps or web interfaces, without depending on how input is collected or results are shown. Separating the core logic of your code from user interactions makes testing, maintenance, and collaboration much easier. When computational parts are isolated, you can test them directly with sampled data without simulating user behavior. This clear separation also lets you update the user interface or change algorithms independently. In a team, it allows different groups to work in parallel on user experience and core logic, as long as they respect the boundaries between them. Python code. Cleanly separating logic. Separate user interaction from core computation by having one function handle input and another function perform the calculations. The input function should collect and validate what the user provides, then pass that data to a computation function. The computation function should focus only on processing data and returning results without directly asking the user for anything. This approach keeps the logic reusable and easier to test, and usually only standard libraries are needed to implement it. This function converts a distance from miles to kilometers using a fixed conversion factor of about 1.60934 kilometers per mile. It takes an input value in miles, multiplies it by this factor, and computes the equivalent distance in kilometers. The function then returns this kilometer value so it can be reused whenever a miles to kilometers conversion is needed, without requiring any direct user interaction each time. This function computes the total distance of a round trip by taking the one-way distance in miles as its input. It doubles that value to account for both the outgoing and return journeys, and stores the result as the total miles traveled. The function then returns this total distance, providing a simple way to calculate round-trip mileage without causing any side effects or requiring user interaction. The function starts by telling the user it will convert miles to kilometers for a round trip, then asks for the one-way distance in miles. It prompts the user to enter this distance as a number, such as 12.5. If something goes wrong while reading the input, the function automatically uses 12.5 miles as a default value. Finally, it converts the input from text to a floating point number so it can be used in later calculations. To find the round-trip distance, we first use a function that doubles the one-way miles, giving the total miles traveled there and back. We then pass this total distance to a conversion function that changes miles to kilometers. This process provides the round-trip distance in both miles and kilometers. Having both units makes the result easier to present and use in later calculations. The program first displays the one-way distance in miles using the stored one-way value. It then shows the round-trip distance in miles based on the total distance value. Finally, it prints the round-trip distance in kilometers, rounding this value to 2 decimal places to keep the output clear and precise. The main distance converter function handles user interaction and coordinates the conversion process. It asks the user for a distance in miles, uses helper functions to convert that value to kilometers, and then shows the result. By delegating the actual calculations to separate functions, the design keeps the mathematical logic clean, reusable, and independent from the user interface steps. This script shows how to separate user interaction from core calculations. It asks the user for a one-way distance in miles, then computes the round-trip distance in miles and converts it to kilometers using a standard conversion factor. The program displays the original one-way distance, the total miles for the round trip, and the total kilometers rounded to 2 decimal places. By keeping input and output separate from the calculation functions, those functions remain reusable and focused on pure computation. Reusing functions effectively. Calling functions frequently. Functions are not just for large tasks. Skilled programmers also use them for small, common operations. By calling functions frequently, you rely on reusable, well-defined pieces of code instead of rewriting the same logic. In a program that processes customer orders, short functions for things like email validation, date formatting, and discount calculation may be used many times throughout the code. This reuse keeps behavior consistent and makes updates or fixes easy because changing the function once improves every part of the program that uses it. Frequent use of functions changes how you structure your programs, shifting from long, detailed code to building solutions by combining smaller operations. For example, in a data analysis script, each step, such as cleaning data or summarizing results, can be a separate function, so the overall flow reads more like plain language. Because these functions can be reused in many different contexts, they become more valuable and efficient over time. By calling them in various scenarios, you get more benefit from the effort you invested in designing them well. Frequent function calls become especially important as your program grows and gains new features. For example, a simple appointment booking app might later need reminders or cancellations. If you have already written functions for tasks like checking time conflicts or formatting details, you can reuse them instead of writing new code. This reduces duplication, keeps behavior consistent, and turns your code base into a dependable set of well-tested functions, rather than a messy collection of one-off solutions. Python code, calling functions frequently. In this lesson, we focus on using small helper functions often whenever a task is repeated, so the code stays simple and readable for beginners. By centralizing repeated behavior into one helper function, a single change to that function can automatically update how the program works in many different places. This approach keeps the overall design clean and easy to understand. If an external library is required, you can install it with the appropriate package manager command before running the code. We define a function that takes a first name and a last name and returns a consistently formatted full name. Inside the function, each name has extra spaces removed and is converted so that the first letter of each word is capitalized. The cleaned and capitalized first and last names are then joined with a space between them. This ensures that customer names are always stored and displayed in a uniform format throughout the application. This function determines a discount based on the total order amount. If the order is at least $100, it returns a 20% discount. If the order is at least $50 but less than $100, it returns a 10% discount. For orders under $50, it returns 0, meaning no discount. Centralizing this logic in one function makes it easy to adjust the discount levels and percentages later. This function first formats the customer's name using a helper so the style is consistent. It then calls another helper to determine the discount percentage from the order total. Using that percentage, it calculates the final amount the customer owes by applying the discount to the original total. Finally, it builds and returns a short summary sentence that includes the formatted customer name and the discounted total rounded to 2 decimal places. We create a list of orders where each order is stored as a tuple containing the customer's first name, last name, and the total dollar amount. Organizing the data this way makes it easy to loop through all the orders and apply helper functions to each one. This structure keeps the data clear and simple while allowing the same functions to be reused with different order information. As a result, we can process each order in a consistent and straightforward manner. We begin by printing a short header to introduce the list of new orders. Then, we go through each order, separating the customer's first name, last name, and total amount. For each order, we call a function that builds an order summary using this information. That function formats the customer's name, figures out any discount, and calculates the final amount after the discount. Finally, we print the summary line so we can see how much each customer will pay. We begin by printing a header to introduce the monthly report highlights. Then we go through each order, pull out the customer's first name, last name, and total amount, and pass these details to a function that builds the order summary. This function formats the customer's name, applies any discount, and creates a single summary line. Finally, we print this line with a consistent report label so each entry in the report has a clear, uniform format. This script shows how helper functions can simplify repetitive work in processing customer orders. It uses shared functions to format customer names consistently, calculate discounts from order totals, and build order summaries. When the code runs, it applies rules such as larger discounts for higher order amounts and prints a summary for each order. the same functions are reused to generate both a list of new orders and a monthly report, making it easy to update the logic in one place and keep all outputs consistent. Eliminating repeated code. Defining functions helps eliminate repeated code by putting shared logic in one place instead of copying it many times. When you repeat the same steps in different parts of a program, you create multiple versions that all need to be updated and debugged separately. For example, if email validation is written out on every screen that needs it, any change to the rules must be made in each copy. By moving that logic into a clearly named function and calling it wherever needed, you centralize the behavior, reduce errors, and make the program easier to maintain. Using functions to remove repeated code makes software much easier and safer to maintain over time. When the same logic is scattered in many places, updating it becomes risky and error-prone. By putting shared behavior into a single function, you can change it once and know every part of the program stays consistent. For example, a financial app that uses one shared function for discount rules can quickly adapt to new policies while keeping all components aligned. When you see the same code repeated, it usually means there is an underlying idea that should be turned into its own function. Giving that function a clear name makes the code easier to read and understand. For example, instead of repeating the same data cleaning steps in every analysis, you can create one shared cleaning function. This reduces duplication, keeps behavior consistent across analyses, and makes the overall system more robust and easier to maintain as you improve that function over time. Python code, eliminating repeated code. This lesson shows how to remove repeated code by creating simple helper functions. You first look at logic that is duplicated in several places, then refactor it into a single reusable function. The example stays beginner-friendly and uses clear printed output, so you can easily compare the original repeated code with the cleaner, refactored version. This line is a placeholder comment reminding you to install any required Python libraries with an appropriate command before running the script. It indicates where you would add an installation step so that all external packages are available. Including such reminders helps keep the code portable and ensures that all dependencies are properly set up for successful execution. We begin by defining the prices of 3 items individually. The first costs $19.99. The second costs $5.49. And the third costs $3.50. This simple setup shows that each price is specified on its own, which works, but leads to repetitive definitions. It prepares us to later refactor this approach into a more efficient way of handling multiple item prices. We start by setting the tax rate to 7%, then find the subtotal by adding the prices of the 3 items. To get the total with tax, we add the subtotal to the subtotal multiplied by the tax rate. In this method, the tax calculation is written out directly inside the overall expression for the total. In this step, we calculate and print the total cost including tax using the same calculation logic as before. We combine the subtotal and tax by multiplying the subtotal by the tax rate and adding that amount back to the subtotal. The result is rounded to 2 decimal places for clarity before being displayed. This example shows the outcome of using repeated logic before it is later refactored into a reusable function. We define a function called calculate total with tax to avoid repeating the same tax logic in multiple places. This function takes a subtotal and a tax rate as inputs. Inside the function, it computes the total by adding the subtotal to the subtotal multiplied by the tax rate, which applies the tax. It then returns this total amount so the same calculation can be reused wherever needed without duplicating code. We begin with a groceries subtotal of $28.98, which is the cost before tax. We then use a function that takes this subtotal and the tax rate, calculates the tax, and adds it to the subtotal to get the total cost. Finally, we print the total groceries cost, rounded to 2 decimal places for clarity. This shows how a reusable function can handle the tax calculation and avoid repeating the same code. We begin with a hardware subtotal of 54.25. Then use a tax calculation function that takes this subtotal and the tax rate to compute the total cost. The function adds the appropriate tax to the subtotal, providing a reusable way to handle tax calculations. Finally, we display the total hardware cost, rounded to 2 decimal places, so the result of using the function is clear and easy to read. We begin with a clothing subtotal of 39.6, which is the cost before tax. To find the total cost including tax, we call a function that takes this subtotal and the tax rate, then adds the appropriate tax amount. The function returns the final total, and we then print this clothing total, rounded to 2 decimal places for clarity. The code prints a message explaining that the same tax calculation logic was used 3 times without copying the code. This demonstrates how putting repeated logic into a single function avoids duplication. As a result, the program becomes more efficient, clearer to read, and easier to maintain or update in the future. This script shows how to avoid repeating the same code by using a helper function to calculate totals with tax. It first computes the total price of 3 items by directly repeating the tax calculation. Then it refactors this by defining a function that takes a subtotal and a tax rate and returns the total with tax. The script reuses this function for groceries, hardware, and clothing, applying the same logic without duplication. When run, it prints results that compare the repeated calculations with the function-based approach, emphasizing the improved efficiency and clarity from reusing the function. Organizing function files. As your programs grow beyond a single file, it becomes important to organize your functions carefully. Group related functions together, much like keeping similar tools in labeled drawers, so you can quickly find and reuse existing logic instead of rewriting it. For example, you might keep data handling functions in one place, calculations in another, and formatting functions in a separate area. This kind of structure makes it easier to locate what your code can do and helps streamline the development process. Organizing your function files well lets you reuse them across many projects instead of rewriting the same code. When you notice functions that are broadly useful, such as input validation or unit conversion, place them in their own file or module so they are easy to import. Over time, this collection becomes a small library of reliable tools you can use in different contexts, like data cleaning and analysis or authentication in web applications. By centralizing these shared functions, you can update and fix them in one place and have the improvements automatically benefit all your projects. When organizing function files, aim for a balance between having clear, focused files and avoiding excessive fragmentation. Do not put every tiny function in its own file, but also avoid stuffing many unrelated functions into one large file. Instead, group functions by their domain or responsibility, such as keeping all payment-related functions together in an online store. Clearly separate public functions intended for reuse from private helper functions. Revisit and refactor your file organization over time so it stays clear and easy to maintain as the project grows. Python code, organizing function files. This lesson focuses on organizing your code into simple, logical modules so you can reuse functions across different projects. You will see how to keep shared helper functions in separate files and then have one main script that imports those helpers when needed. The goal is to keep everything beginner-friendly while clearly showing which file is responsible for which part of the program. By the end, you should understand how separating code into modules makes your projects cleaner, easier to manage, and more reusable. This comment explains that if external libraries were ever needed, they could be installed with a package manager. But for this particular script, the Python standard library is enough. No extra installations are required. This highlights that the code is simple, easy to run, and depends only on built-in Python features. We begin by importing the temp file module from the standard library, which provides tools for creating temporary files and folders. These are useful for handling data that is only needed while the program runs. In this script, we use it to create a temporary directory that stores example module files. This directory and its contents are automatically removed when they are no longer needed, helping keep the system clean. We begin by importing the operating system module from the standard library, which lets our program interact with the underlying system. In this script, it is mainly used to manage file paths. By relying on this module, the code automatically uses the correct path separators and conventions, so it can run properly on different operating systems without modification. The code uses a standard library tool called importlib utility to load modules dynamically from file paths. This means you can import Python code that is not in the usual module search locations. It is useful when you want to keep code in separate files and load them only when needed. This approach helps make your programs more modular and easier to reuse. This function creates a new module file with the given content. It first builds the full file path by combining the directory and the file name, then opens the file in write mode using UTF-8 encoding. Within a safe context that automatically closes the file, it writes the provided text into the file. Finally, it returns the full path to the new file so that it can be used later, for example, to import the module. This function dynamically loads a module from a given file path. It first creates a module specification using the import library, which holds the information needed to load the module. Using this specification, It then creates an empty module object and executes the module's code inside it. After execution, the function returns this module object so its functions and attributes can be used. We begin by creating a temporary directory using the temp file module to hold our example module files. In this directory, we define a module called conversions that contains reusable measurement conversion functions. One function converts inches to feet by dividing by 12. Another converts miles to feet by multiplying by 5,280. And a third converts Fahrenheit to Celsius by subtracting 32, multiplying by 5, and dividing by 9. These functions are intended to be shared and reused across multiple projects. This module defines helper functions that format measurement results for display in a consistent way. One function takes a length in feet and returns it as a string with 2 decimal places followed by the word feet. Another function takes a temperature in Celsius and returns it as a string with 1 decimal place followed by the words degrees Celsius. Together, these helpers standardize how measurements are presented across a project. We first create a conversions module file in the temporary project directory using a helper function to write a file named conversions.py that contains the conversion functions. This keeps the conversion logic in its own module so it can be reused in other projects. We then create a separate formatting module file in the same directory, again using the helper function to write a file named formattinghelpers.py with the formatting functions. By separating conversions and formatting into distinct modules, we keep their responsibilities clear and make the code easier to maintain and reuse. The code uses a helper function to dynamically load the conversions module by creating a module specification, building an empty module from it, and then executing the module's code so its functions become available. It applies the same process to load the formatting module and access its helper functions. This dynamic import method makes it easy to manage modules and reuse them across different projects without hard-coding their imports. We begin with a board length of 96 inches, which is the measurement we want to convert. To change this value from inches to feet, we use a conversion function from the conversions module that divides the number of inches by 12. The function returns the equivalent length in feet, and we store this result so it can be used in later calculations or for display. We begin by setting the walking distance to half a mile, which is the value we want to convert. Then, we use the miles to feet conversion function from the conversions module to change this distance from miles into feet. The converted value is stored for later use, so we can work with the distance in feet, which may be more convenient for certain calculations or presentations. We begin by setting the outside temperature to 77 degrees Fahrenheit. Next, we use a conversion function from the imported module to change this value into degrees Celsius. The function applies the standard Fahrenheit to Celsius formula and saves the converted value as the Celsius temperature. We first format the board length using a helper function from the formatting module, which takes the length in feet and returns a string with the value shown to 2 decimal places. We then apply the same helper function to the walking distance, again starting from a value in feet. Using this single function for both measurements keeps their appearance consistent and easy to read. The code uses a helper function from a formatting module to turn the outside temperature into a clean, readable string. It first works with the temperature in Celsius, which was already converted from Fahrenheit, and then passes this value to the formatting function. The result is a neatly formatted temperature string that is ready to display or reuse. This shows how shared modules can make output formatting simpler and more consistent across a project. We begin by printing a header to show that the results come from organized, reusable modules, which sets the context for what follows. We then display the board length, using shared conversion and formatting functions to present the measurement clearly. Next, we show the walking distance, reusing the same functions in a different situation to keep the formatting consistent. Finally, we print the outside temperature, demonstrating that these modules can handle different kinds of measurements while keeping the output accurate and easy to understand. This script shows how to organize Python code into reusable modules. It creates separate modules for conversion functions, such as converting inches to feet, miles to feet, and Fahrenheit to Celsius, and for formatting functions that present lengths in feet and temperatures in Celsius. The main script dynamically imports these modules, uses the conversion functions to process a board length, a walking distance, and an outside temperature, then formats the results and prints them. Overall, it demonstrates how separating related functions into modules makes code easier to reuse across different projects. In this lecture, you learn to design functions that perform a single clear task to improve readability, separate user interaction from computation by structuring code into helper functions, and reuse functions across different parts of a program to reduce duplication. In the next module, Module 6, we will go over strings and text. Thank you for your attention. See you all in the next lecture.